we can move on to the next talk, which is going to be given by Ornthal Tucker. Hopefully I pronounced your name right. Please feel free to correct me as you come on. And they'll be talking about investigations on solar wind implementation in the lunar regolith and volatile stability.
Thanks for the opportunity to talk. Yes, Orenthal Tucker is correct. Go by OJ. And so yeah, I'm also part of the leader team, as Bill talked about earlier. And I want to talk about solar wind implantation into the lunar regolith and the retention of volatiles by the lunar regolith. So I'll review solar wind implantation and talk about some of the theoretical and experimental work that has been carried out by some of the leader scientists. And so here is just a nice schematic here. Really, the solar wind is an important source of volatiles to, the moon and just airless bodies in general. So there, micrometeoroids are also a really important source, but this talk will focus on the solar wind. And it really just induces global scale chemistry in the lunar environment. And so this depiction here just shows how ions in the solar wind, they can come in and plant into the lunar surface. And then those ions can chemically react to form various volatiles. We're interested in like molecular hydrogen and hydroxyl and methane, which can diffuse out into the exosphere. So it's really a plasma surface volatile connection that we're really trying to investigate here. Also, as Bill talked about earlier, you can have these localized cycles like at the pole regions. And so you can see here where you have the white is sort of indicating regions where water might be more stable. And so you can have sputtering of these regions, which might even drive local cycles. And there's some observations of this, widespread hydroxylation of the surface. So some observations have been done by Cassini here and other missions, but here we'll talk about the M-cubed observations. So the top figure is just showing how that hydroxyl content, is recognized through the 3-micron absorption feature. And it can't distinguish between whether it's water molecules or hydroxyl molecules, but the top figure is just showing how there's a diurnal change in that signature over a lunation. So you can see the one on the left is showing like in the morning, and then noon, and then the evening, with the darker colors representing more absorption and the lighter colors showing less absorption. Also, in a work by Lee et al. 2017, they took averages over the surface, demonstrating that there's also a buildup in content at high latitudes. And some more recent work by Casey Honniball shown here, using the Sophia telescope, which can looked at 6 microns absorption feature, which can distinguish between water and hydroxyl, and just showing the profiles of water compared to the M-cubed hydroxyl shown here. So there's been a lot of evidence of implantation leading to the formation of hydroxyls throughout the lunar environment over the years. To go into a little bit more detail about the process, so solar wind implantation has been thought about, for several years, and so in this process, the energetic ions from the solar wind, they can implant into the surface. If we're thinking about protons, but also other ions, as they come into the surface, they can excite electrons of bound regolith atoms. They can also break bonds, right? And they can implant into the surface. And so when they break bonds, they can break like a hydrogen bond. That hydrogen can subsequently diffuse by, forming metal stable bonds with oxygen as it comes to the surface. And by one process, it can degas from the surface is through recombinative desorption. So 2 H molecules can meet up and come off as H2. And we have some, observational evidence of this. Of course, in the surface, we have M-cubed observations. There were some observations by Cassini, also by the Deep Impact mission. And in the exosphere, we have observations from Chase that occurred in the magnetotail and LAMP of observing molecular hydrogen. And so when you have observations of the proton flux coming in, and the hydroxyl signature or water signature, where we can really connect the dynamics of this cycle to understand it much better. So really, we're trying to understand how microphysical processes affect, that global hydroxylation distribution and also what's released into the exosphere. Some important properties to understand are diffusion, activation energy, chemical formation rates, and also how effects like surface defects, vacancies, physical trapping mechanisms, or chemical trapping mechanisms like dangling bonds will affect the diffusion of the hydrogen out of the surface. And this schematic here of the diffusion coefficients just shows that we really don't understand this process well for, various forms of silica with different impurities and defects, but we understand it even less in the native environment of the moon. But some experiments by Fink et al. Shows that for silica under irradiation, it really can lower the diffusion coefficient compared to like a pure silica content, and that can result in the retention of hydrogen over time. And so this is one of the things that leader scientists have been looking at. And notice the order of magnitude change in diffusion there. So just briefly, excuse me for the cough, the volatile retention time, it depends on temperature, which is shown nicely here by some work done by Bill Farrell, defect sites, which can be represented by like an activation distribution of energies, and the proton flux. And that's what these two graphs are showing here. So it's showing that, for times above that dashed line on both plots, the hydrogen is retained over illumination, so it can build up. However, near the 2 minutes, okay, near equatorial regions, you can see that it diffuses less than illumination, so you can get a diurnal effect. We can put this into like global models to examine, instead of like a short time period, we can look at a longer time period over several lunations examining steady state. And you can see, depending on that activation energy, you can release too much hydroxyl content or hold on to too much, or you can release just about the right amount to compare with observations. And that's what these plots are shown here. It also affects what's released into the exosphere. So these plots are the gas distribution in the exosphere of H2 that's released out. And so if that activation energy is too large, then it affects the degassing. It is diffusion limited, and so it restricts how much is released to the exosphere, which is another important constraint. I'll just skip past this part here, but this is also demonstrating that, of course, you would have these effects as you pass through the magnetotail and magnetosheath, especially for light species like hydrogen, which can escape on really short time scales. So you can, these dynamic effects can be modeled and compared to dynamic observations of these different processes. I like to highlight the experimental work here done by Jason McLain, just showing that if you irradiate lunar soils, that you can really, it really retains atoms as OH, and under more irradiation, that absorption band deepens and broadens. Excuse me, I'll take a drink. Okay. And also, so we're looking at the microphysical properties at the experimental level, shown by these experiments here, looking at how the absorption feature changes with radiation, and also diffusion at the atomistic level, using these molecular dynamic simulations that really show this diffusive process from bond to bond, from oxygen bond to oxygen bond, occurs as like a jumping type of mechanism, in which the hydrogen atom then stays at that bond, sort of fluctuating around the oxygen atom until it hops to another oxygen bond. So we can look at these processes at the atomistic level and see how it informs the global observations. Bill Farrell and our dear friend Mike Collier have thought about how we could look at this dynamic process with various lunar experiments. And so, using a combination of plasma spectrometers, IR spectrometers, also sample returns for laboratory experiments, and as well as mass spectrometry, UV observations, and witness place, which somebody might talk about later on today. We can use instrumentations on the moon together to really monitor this process dynamically, to really help better constrain some of the inputs into the models, to understand, right, these valuable resources So in conclusion, the solar wind is really the solar wind interaction with the lunar regolith is really a chemical factory, and the plasma surface interaction is really important process that could lead to vital resources for use in the lunar environment. And we're continuing experiments and modeling to understand this process. And I'll leave it there because I'm probably running over.
Just about over. So thank you for that and great talk. Um, it's really interesting to see all that stuff, and I know there's always been quite a bit of debate of how much hydrogen or oxygen some of those particles come from either the ionosphere or the solar wind. So it'll be interesting to see um, how that changes and what we look at as we start looking at these things.
Yeah.
Um, so great talk. Thank you.